The exciting thing about mass spectrometry is you can get so much data in a single run. And if you're taking multiple runs, if you're going for lipidomics, proteomics, metabolomics, you can get millions of data points for a single sample. And of course you need 40, 100, 1,000 samples to get good data. That is a lot of data. And what you don't want to do is you don't want to look through all that data by hand. Many of the tools that are available right now will not actually help you get at your biological question, and that's what we want to talk about today. You have a particular biological question. How do you get your software to focus on the molecules that matter for that question? That's what I'm going to show you about today. Stay tuned. Okay, when we're working in mass spectrometry, the abundances of the molecules, that's good. The molecular identity of those molecules, that's good. But that's not the first question we have to answer. The first question we have to answer is, what is the biological problem you're trying to solve? Because that's going to help us focus on finding the molecules you care about. So, are you trying to identify liver disease? Are you trying to identify the presence of a heart condition? Are you trying to come up with an indicator for Alzheimer's? Are you trying to understand the chemistry of Alzheimer's? What's the biochemical makeup? Are you trying to detect cancer? These are all interesting questions. They're biological questions. You have to identify first what it is you're after. The more specific you are, the better we're going to be able to help in teasing out those exact questions and what the molecules are that make a difference. So that's our first step. Okay, once you know your biological question, there are three issues I want to discuss with you that we're going to need to be able to zone in and get on those molecules that you need. The first issue is most of the tools that are currently available are going to measure rather than answer questions. So they measure, they report the measurements, and then they let you figure out how that relates to your problem. Okay, the second issue is we're going to organize our data into two sets, A and B. Because by comparing these two sets, we're going to identify what the molecules are that are different, and then we're going to be able to identify what's important to separating these two sets. Once we've decided the two sets, then what we're going to do is we're going to have the computer calculate what we call a decision value. The decision value says for every one of those data points, 500,000, 2 million, 3 million, don't care, it's the computer's problem. Once we've got those data points and we've separated our sets, then we're going to take every one of those data points and say, how well does this data point separate A from B? Is it completely muddy? 99% of the cases. Is it close? Is it separate but close? Or is it a really great data point that really tells us a lot? This is very different than this. These are the molecules we're looking for. So those are the three steps. We don't want to just measure. We want to separate to A and B, and we want to compute decision values for every one of those data points. As I go through and describe this to you, you're going to have questions. That's okay. Please use the comments below to ask those questions. If you ask those questions, then in future videos I can clarify for you. The other thing we want you to do is like, subscribe, click the little button for the bell, anything that will let you know when we've got more information for you, more details. We can't do all the details in one video, so we got more coming. Make sure you like and subscribe so you get that. The primary focus of a lot of software tools is to measure and report. So one of the things tools will first do is they'll put up a spectrum. There we go. We've got the abundances of all the M over Z's of all the molecules that we found. Great. Now, let's suppose what I'm doing is a peptide scan and I want to go from 0 to 5,000 Daltons is the mass of the molecules I'm looking for. And I want to go a resolution of 1/10 of a Dalton. Okay, that's 50,000 data points per sample. Now, if I'm also doing chromatography or ion mobility, that adds a whole nother dimension, and this is where we get into our 500,000 data points. Now the problem we've got is, let's suppose I have a really good screen, it's 4,000 pixels across. I'm going to take 50,000 data points and cram them into 4,000 pixels of spectrum. That's not going to work. Now, everybody knows this. So the first thing they do is they give you a zoom. Okay, I can take a section of the spectrum and zoom in on it. Which part of the spectrum should I zoom in on? No guidance. Okay, well, if I don't have any guidance, then what I'm going to do is I'm going to go through this spectrum by hand over and over and over again until I find something that's interesting. And remember, I don't have one tissue sample. I don't have one subject. I probably got 40, 100, maybe 1,000 if I'm doing a big study. I've got a lot of data, and I cannot go through all this stuff by hand. So, that's our first problem. If you just measure and report, I've got an almost insurmountable problem of how to make sense out of this data. Now, we do have tools that are trying to help us find the things that are of interest to us. The most common technique is find the ones with the most abundance, the high spikes. Okay, that's a relatively easy algorithm to implement and not necessarily the right one. The things we're looking for that actually answer our biological questions are not always the highest spikes. So we've got to have something better. Okay, let's do a thought experiment. Let's suppose what we're trying to do is we're trying to find a breast cancer tumor, and it's maybe 1 to 2 centimeters, which makes it about 1 gram in mass. Average woman is about 70 kilograms. Okay, that makes the mass of the tumor compared to the mass of the woman about 1/70,000th. So if we're trying to detect this, say for example by taking blood serum samples, we got 1/70,000th or 0.002% of that blood sample will contain molecules from this tumor. Now, that's a rough estimate, but basically that is not going to be in the big abundances. That's going to be in the little abundances. We're not going to catch this by taking the bigs. Okay, let me take you an example drawn from real life. One of my colleagues had a grad student who was interested in the biomarkers for various stages of breast cancer. Okay, so she got 39 patients, drew the blood, extracted the serum, ran it through the mass spectrometer. Now, 39 patients and roughly 500,000 data points per patient. Well, that comes out to 19 million data points for all the data. Now, she didn't have any of the software to find what's important, so she actually spent 1.5 years, a year and a half, looking through this data by hand, trying to identify things that would discriminate the various stages of breast cancer. Now, after a year and a half, she was successful, and she was able to find 10-ish or so biomarkers. We're great. We love that, because what that means is the data is there, the information is there. But 1.5 years to find it, that is not good. We need a better solution. All right, let's switch to issue number 2. Issue number 2, what we want to do to help us focus in on the particular molecules that matter is separate our problem into 2 sets, A and B. You've got a set of examples with their mass spectrometry for set A and a set for set B. So for example, people who have liver disease, people who don't. People who have a heart condition, people who don't. People who have Alzheimer's, people who don't. Now, these are really general questions. I don't recommend them. What I recommend that you think really hard about the precise individual things you want to look for, but the idea is the same. Set it up so that you have a contrast. It's basically a controlled experiment. Set it up so you have a contrast between 2 sets, and then we're going to find what's different. Because what's different, those are the molecules we care about. We've identified our biological problem for our software by picking set A and set B. And the differences between these 2 sets relate specifically to our biological problem. We've done that. All right, now the next step is, in issue number 3, we've got to compute a decision value. And a decision value, we're going to take every one of those 500,000, million, 2 million, 3 million, however many there are, every one of those data points, and we're going to take all our examples for those data points, and we're going to say, how well do they separate? Decision value is a measure of how well they distinguish A from B. Okay, so case number 1. Case number 1, A and B is overlapped. A and B is overlapped a lot. This is a really stinky data point for our particular problem. This data point will tell us almost nothing about our problem because the A's and the B's are all mushed in together. This is 99.99% of all of your data points, because most of what you're going to see in a blood sample, tissue sample, etc. are molecules of ordinary housekeeping. That's the vast majority, because if it isn't, you're dead. Okay, case number two. Case number two, they overlap just a little bit. Just a little bit. Now this is not a bad data point, because we can separate the A's from the B's. It's just we have a little confusion in here. Have a little confusion. So there are some cases that this will not be able to sort out. So we're going to give this a decision value of, let's say, 0.9. Not too bad. All right, case three. Case three, the A's and the B's are separate, but they're really close together. All right, the problem with this is if there's any noise or any error or any slippage in our data, they're going to overlap. So we're going to give this a decision value of something around 1. They're separate, but not well separate. Case 4. Now they're separate. The A's and the B's are completely disjoint and there's a nice big gap in the middle. Here's why we love the gap. A little bit of error here, a little bit of error here, does not matter. Does not matter. Still separates. Still A and B are completely distinct if you look at this data point. We love this data point. This is telling us a whole lot about how A is different than B. So we're going to look for these. Let's summarize where we are. So what we've got is we've got massive amounts of data. Lots of it. And we've got to find out what's important to our biological question. Now, a common technique is put up the spectrum. Well, that's a lot of manual labor. And we're talking about millions and millions of data, pieces of data that we've got to sift through. This is not a great idea. So what we're going to do is we're going to do A-B comparison. For our problem, we're going to get a value, a set, and a control set. A versus B. Two different things, and we're going to compare them. Now, we're not comparing for statistical significance. We'll talk about that in a later video. What we're comparing for is decision value. How well does this feature separate A from B? So we get sort of a good decision or a really clear decision. That's what we want. We're going to calculate this decision value. Now, once we've calculated that decision value, we're going to pick the largest decision value. Not the largest abundance, the largest decision value. Because that's going to tell us the molecules that make the most difference between whatever we set up as set A and set B. There you have it. What we've done is we've separated A and B. We've focused in on some molecules using decision values. This is great. Now, what I understand is I glossed over a huge amount of how we calculate this, how we cast this into software. I didn't cover any of that. I understand. So what I need you to do is I need you, number one, ask questions. In the comments below, ask your questions. Number two, I need you to like, subscribe, hit the notification bell, all those things, because in future videos we're going to come back and tell you the actual algorithms, the equations that make this work so that you can do this for yourself. So, we'll come back to you later. We hope to talk to you and continue to inform you about how we focus mass spectrometry where we care. Thank you for watching.